Hello, RMC teams and space enthusiasts. Mike here from EDT at ISU. A few weeks ago, we spoke with Iowa State's Lunabotics team. It was a great way to get to know fellow engineering students from around the nation.
As first-year entrants into NASA's robotic mining competition, we really appreciate the insight that ISU's Lunabotics team was able to share with us, particularly some of the modes of failure they encountered where they are in position, and hopefully we were able to share some of our knowledge with them. Enjoy.
Hi, would you guys like to begin soon?
Yep, we're good for that. So, I guess just a little, if you want to start with some background on our team, we entered the first year that there was the Lunabotics mining competition. Sorry, getting a response from one of our guys. So we entered the first year the competition existed as a senior design team, and it went all right, but we ended up having a mechanical failure, so we didn't really do that well on the competition side. After that, we decided to make it a student organization. Once that happened, we were able to more easily funding from sponsors and get involved rather than just a crop of seniors that graduates and moves on. So since that happened 3 years ago, we've consistently had around 20 active members and have designed 4 robots so far. Second year, we also had a big mechanical failure. The third year was 2 years ago. We got first place on the mining, first place on outreach, first place on communications efficiency, and then second place on the And then last year, got first in mining, third on outreach, and first overall.
Yeah, that's pretty impressive. We've definitely looked at your stuff. You know, you guys are the premier society, I guess, when it comes to this competition. So we know you did your background work because we also were looking as a new society and how to do this, and we came across some papers. I don't know if you've looked at them. They're like lightweight lunar excavators, and they like pretty much the exact design that you had, the wheel bucket or the chain bucket excavator. So I'm glad you could join us and have this chat. Would you like to go into a little more detail on like how your failures happened and what was your process afterwards and how you improved your design year by year?
Sure. So the first year, I'm not intimately familiar with the first 2 years. I was still in high school at the time. But the first year, if I recall, it was a motor failure. Does that sound right, Nathan?
I don't know.
The first year we had open sprockets, I know. And we ended up getting lots of dust caught up in there, and that
was the chain binding, I think.
The chain ended up binding, and then we burned out a motor.
When you have chains in there, there's so much friction with that material, it just tears it all to shreds.
Also, the first year, another thing we had was we had basically a snowblower set up. We thought, you know, it's really effective at moving snow. It'll probably be really effective at moving the BP1. Turned out to be not quite as successful as we had hoped. Whether they'll tell you it or not, there are rocks in the material. So if you're not designing around the fact that you're going to get anywhere from pebbles to, you know, a couple inch in diameter rocks, those are deeper. They're not on the surface. But if you don't design with that in mind, you're going to have some unintended consequences in your robot design. The second year, so the first year I think we ended up spinning around in circles because we couldn't use one side of our tracks.
What's the second?
Oh shoot, that was the second year. I'm sorry. It all blends together, especially since I wasn't around. One of the things we learned was cover up any sprockets, or better yet, just don't have them in general.
Chains.
Yeah. And then our other failure was 2 years ago. We were driving around. We were doing pretty well. We'd collected some material. They estimated about 40 kilograms of material, so it was a pretty good load. And on the way back to the bin to dump, one of the
the wheels on the truck.
Yeah, one of the wheels on the track came off, which rendered the robot unable to move. So we could spin around in circles, and we couldn't deposit the material, so we didn't get any points, and we did really poorly overall. Finally, the third year, we got our track system figured out and working really well, and that's when we got first place on mining. So after that, our instructor encouraged us not to just ditch last year's design and start fresh, but go back, really think about what we did, learn from it, and design a better robot in the future.
Hi, David, this is Tim Muellerson, also part of the RMC here at EDT. What you said you're keeping the same design as last year. What did you find that you didn't do too well with last year, with your design in particular?
So last year our design overall was very successful. Mechanically, it's essentially the same as what we've used basically the same thing for 2 consecutive years. The biggest difference we had was weight and weight reduction. So 2 years ago, so the first time we had a successful robot, it was called RD3 for future reference. We had a 42 kilogram robot. Last year we had a 35 kilogram robot. And when you look at the scoring breakdown on the competition, really it all comes down to how heavy your robot is. You can have an 80 kilogram robot that can go and collect 10 kilograms of regolith, but that won't matter because somebody way lighter than you collected 3 times that easily. So the goal is always to break even on points. If you can break even, you're going to do pretty well in the competition overall. We came pretty close last year. I don't think we didn't quite make it, but that's something that we kind of aim for. So then this year, we're doing more optimization, primarily reducing the weight, but maintaining the same collection capability and ability to move.
It's interesting. Are you guys have gone into autonomous motion as well, correct?
We worked on that last year. We got the furthest in autonomy of all the teams at the competition. By that I mean we were able to collect material and we're on our way back before our autonomy failed.
Okay. Yeah, I mean, I think that's, for now, that's what I have. Do you have any questions for us?
I don't have any explicit questions. So I think I saw you guys had a design up. Do you want to pull that back up and we can maybe give you a little feedback on it, some things you might want to watch out for?
Yeah.
So, no, some.
So we did actually go to chain drive for the for most of the mechanism. Our conveyor belt is going to be, our bucket conveyor is chain driven. Our wheels are chain driven as well, but those are enclosed. Yeah, I mean, what you said about the exposed chains is difficult. How do you drive your conveyor if you don't use any type of chain?
So the trick to
It's basically direct drive.
Yeah.
So we have a motor connected to a planetary gearbox, and then that goes straight to what we call the squirrel cage, which is what powers, which turns the belt.
Yeah. So this was the scroll cage we used last year. This is just a 3D printed mock-up, but it's a very open design, which allows us to get it right down there in the BP1 without worrying about having issues with, it's designed so that BP1 will get in there and
Fall right out.
fall right out, yeah. So we used the same basic design for our tracks and for our conveyor collection system.
Now, did you make those scroll cages yourself? Did you have them?
Yeah, we have a CNC facility on campus that we used for that.
Okay.
Oh, sorry.
You might be all right with the open chain on the gear or on the wheels, but I'd definitely look at something else as far as your conveyor is going.
What number chain did you use? Do you remember it all? Was it the small 35 chain? Yeah, I mean, it's almost, I don't want to say it's too late to change our design at this point for what we have currently existing, but it would be very difficult to go to a direct drive at this point. We would still need the chains. We're going to use the chains to move the conveyor, the buckets themselves.
And
we don't have access to CNC.
Oh, so you don't have a belt conveyor? You have a chain conveyor?
yeah. Alright, so we just had, this is Brian. Brian is our project director. He's done a lot of machining for us the last year. So as far as your chains, your collection system, honestly, I don't think that the size of your chain will matter too much. Just the fact that you're using them and you're getting them
a large chain will
down
work
in there
better than a small one.
Yeah.
It'll be harder to hop off, but just being open like that, you're still going to run into issues, I think, unless you go with a really big chain, in which case it's effectively our system.
Yeah.
Another thing to consider is the judges. They have points to give out for dust tolerance, and those are going to prevent them from awarding points. Because whenever they see an open chain, they're gonna know something's gonna go wrong. So just to give you an idea of what the judges are looking for, an open chain is definitely not something they prefer to see. In my experience,
Yeah.
I can't say for.
I always complain about
So one other question. Is there a possibility of making your buckets any wider? Or bringing your sprocket, your chains in a little bit? How wide are your buckets to begin with?
We have it at 6-inch wide. We were running our numbers off the Bolonev excavation model, so we didn't want to go like higher because that's where we spec'd our dig motor to.
Sure. So if you've got a 6-inch, yeah, this is 8. If you've got a 6-inch bucket, could you bring the gears in an inch on each side, just so that they're not on the far edge of the bucket?
Oh, so what you're saying is kind of bring the sprockets away from the bucket
From the
exterior.
Because if they're at the edge of the bucket, then they're basically at the edge of the channel that you're going to be digging, and they're going to be like entirely always in the material. Whereas if you brought those in an inch, I don't know how much your design allows. I'm just throwing a number out there. Then hopefully the channel that you're digging would keep it out of the BP1.
It's a drive shaft that's going to go all the way through the that upper digging mechanism there. So we can definitely shift those in. The buckets aren't built yet, so.
Yeah, I would do that.
What did you use for materials for your buckets?
So last year we used steel buckets.
Overkill.
They were overkill. We also accidentally ordered the wrong gauge, and it was pretty late in the process, so we couldn't correct that. So we had a very, very good factor of safety, but we also had an extra like 4 kilograms of steel on a robot. This year we're looking at ways of reducing that weight down significantly.
We've also done plastic in the past, and the issues we've had with plastic is that it's very springy and it flings material forward, which the judges don't like from the dust tolerance standpoint, and also we were kind of throwing rocks at them, so they didn't really like that. Plastic ones work really good from a weight standpoint and from an overall strength standpoint, but they're very elastic, and that led to some points issues.
A big thing if you use plastic is to make sure that you get the material choice and manufacturing process done correctly. Where's the
Plastic ones?
So here's a design that we were going to use 2 years ago. So it's tough to show on a camera, but it's a pretty basic bucket. It's got 2 little ridges here for strengthening. Yeah, so this is the mold that we used for a similar one. So these were just strengthening ridges. But when we did the injection molding process, vacuum molding, my bad. We didn't have everything down quite right, and we ended up making some very brittle buckets. And we went and tested it in our testing facility, like the night before, so a Friday night, and we were leaving on Saturday, and we lost probably 15 out of about 25 buckets in like 10 minutes of driving it around.
No, I think it was like digging once or twice.
Yeah.
It was worse than that.
It was very, very bad. So we actually were manufacturing our buckets on the way to Florida. I would not recommend doing so. So if you're were you planning on using plastic or metal?
We were going to go with steel. Steel. I mean, it's simple. We can weld it.
Yeah.
Do you guys have a target weight for your robot?
Our target is under 80 kilograms at this moment. But no, I think we're estimated about 150 right now. 150
pounds, or was that 50 kilograms?
No, 150 pounds. So like 80 kgs is 177.
Okay.
Hey, how does your linear actuator? How's your leverage there?
That's the pivot, so it looks like they got maybe 4 to 6 inches. Maybe 8 based on the scale.
Can you actuate that?
Yeah, we did a little kinematic analysis off that. It's like 8.25, and yeah, we can show you our little workbook. We just spec our actuator, spec our stroke, spec our force. We did like static equilibrium, and then put a factor of safety on that to represent the start. And then we ran our kinematic to see if we got a good dumping angle, and then place it that way. Our distance from the back is 8.25, I think.
Are you lifting the conveyor as well, like we did?
Yeah.
Yeah.
Okay.
How much do you anticipate collecting in in your conveyor or in your hopper?
You mute yourself. Oh. With our container right now.
Yeah. We can't hear you.
For our container right now, we spec to about 30 kg, so that hopefully we can achieve 1 1. But, you know, that's not the case, so we're trying to make it significantly bigger, so we have it spec'd for a full basin to be 30 kg.
Alright, so one other question I have about the conveyor system. How are you taking the material from the bucket into your hopper?
We were hoping to do that off the trajectory at the very top, where it'll be our, like going from rotational to linear velocity, where at the top will be completely this way, and hopefully we'll toss it back. We ran the numbers on how far it should go back, and they weren't very informative per se. We got it, because our thing right now is going pretty fast, because we maybe overkilled our motor just to be safe, because we figured that was a place where we could over-design. So hopefully it should fling it back. We were looking at grain elevators and other types of mechanical designs that do this kind of thing, and so that's how we based it off. That's how we based off design, that it would fling it back into the container base.
And is there going to be a dust shield of any sort on the robot?
Yeah, we haven't included the panels and the closures yet. We'll probably have some type of Lexan or PVC or Lexan with aluminum L angles to try to cut bait. And then that will also reduce the dust pickup, hopefully, if we can get it pretty close to the ground.
Yep.
When it's coming off, it's not going to, like you said, be throwing it in the judge's face, or at least as much as possible.
We've never. Did we have a vertical collection system ever? Was it
2 years ago? Yeah.
Was it vertical? I didn't remember if it was an angle.
Well, RD3?
RD3 has one. The first of this design, pretty much.
Yeah, it was mostly vertical, so we tried to do the throwing it back with the trajectory.
But it could also just be we didn't have a speed spec, right?
Yeah.
Just saying.
Yeah. we've been more successful overall with a bit of an angle on it. So
Letting gravity take care of some of these.
yeah, letting gravity help us out. Shoot, Brian, I forget how do you rotate the hopper or flat?
Just grab it.
You can't do it in all the models. I think you have to be in the other model
Oh.
to move it.
I can't show you right now, but
You have to do it.
when there's so yeah, this will work good enough. We have just a bit of an angle on the conveyor, which lets the material fall out. It also gets thrown a little bit, but we're not relying on it getting thrown as much. And this year we're even backing it up to a steeper, or to a I guess it depends on how you look at it, more angled.
How will that kind of affect your dust production? With now the buckets, a portion was kind of throwing it forward.
Sorry, can you say that again?
How will that affect your dust production when you're digging? Because both some of it is going like throwing forward. If you're more at an angle this way, you get my.
It'll have some effect.
You're throwing that way.
Yeah.
We usually try to dig so that the top of the surface of the simulant is right at the center radius of that wheel there. You can see the screen, right?
Yeah.
So then changing your angle doesn't really affect it too much because you've got your bucket coming up out of the material more or less vertically.
I guess I have another question. Your container. How did you guys form your base?
So the collection hopper. So 2 years ago we used aluminum, and that worked fine. Last year we decided to venture into composite materials. So we had a carbon fiber Kevlar weave that we used.
So basically, both the years with those two different materials, they were functionally great, but we still want to go lighter, just because it doesn't really need to have the structure in it. So I think even last year's was a little overkill.
Last year's was way overkill, but that didn't have to do with materials.
I wanted to try claw.
What did you use for your conveyor belt material?
Food grade PVC belting. ordered off McMaster. They don't give you much information about the specific dealer, or the specific producer. Yeah.
How do you make the buckets?
How do we make the buckets?
The belt.
So we just
Built them.
we cut it to size, and we cut a V in it, and then anti-V, I guess, on the other side. We put the two together, and then we sew them together with spider wire, which is like a high-grade fishing line, if I remember right. Hey, did you look to see if we can get full circles?
Yeah, I'm just worried about putting a whole pattern in it. Be a lot of work. What? That, and if it's not spec to the right size, you can't adjust it without cutting it anyway. It's not lazy, it's... I want to make sure it's done right.
So are you guys working on autonomy for your first year at competition?
Well, we've been actually within the society we have another. It's like within the society we have multiple robotic teams, and one of their teams is the intelligent vehicle design competition. So we're hoping to be able to use some of their work in our competition, but I'd say it would probably be a stretch.
Yeah, as of this point, it's almost too late to.
Sure.
I mean, yeah.
How have you guys been approaching that challenge?
So I think I can do this in Google. We'll see, or in the Google Hangout. I can't remember if there's a way to watch a YouTube video with everyone.
Yeah, you can pull up the YouTube and then screen share.
I guess I can do that, yeah. Give me just a sec.
There's a YouTube app as well.
Yeah, I was looking for that. I didn't, I can just screen share on this side. Alright, are you guys seeing it? Or do you still see the, oh shoot.
Can you screen share, I think?
Just a sec, I have my screen share settings wrong. I'll just do this. Ah, there we go, okay.
It's gonna be really choppy.
I just send them a URL.
Yeah. Let's try the YouTube app.
Yeah, it should be, if you want to give me the...
It just allows you both to stream but sync.
Yeah.
That's a good way to do it.
Oh, there it is.
Oh, yeah, there it is. I got it. Oh. Oh, you had it. I think we lost it. Yeah.
Alright. Give me just a minute. I've never used the YouTube app on this, so I have to figure out how.
Okay.
Probably might want to turn the sound on.
Yeah, turn.
The sound out.
Mute the video.
Mute the YouTube video. So if I just paused it, did it pause for you as well? Just so I know how this works. So we started off with oh my God. All right, so we started off.
We can't hear you.
Okay, so it just we spun around and it was looking for the retroreflective target that we attached to the hopper. Can you hear me? Oh.
You might get muted during video playback.
Check.
Can you hear me? Can you hear me?
Sorry, that was our fault. We got it back.
Okay. Nathan just pointed out a better way that I can do this, so give me just a sec, and it should work fine.
I'm a genius.
Yeah, he's a genius.
How large is your team?
Probably.
It's a hard number to.
Yeah, it varies. Since we're a student organization, it's difficult to just like put a number on it because people come and go, and it's not like a senior design where you're in it. But if you looked at active people, probably 15 to 20.
Minus, several.
Can you hear me?
Yeah.
Fantastic. So it's spinning around, and it was looking for the navigation target with a laser. And then there were two little whiskers on the back that were attached to reed switches.
Yeah.
Once it hits one, and it just stops that side of the track. We designed our robot such that we did not worry about hitting a rock or a crater.
Meaning we were just going to forge the river, basically.
Yeah. So we had a closed loop control, so if we ran over a rock and came off at a weird angle, it would correct itself. So then there are two arcade buttons sitting out on the front. Once those hit the wall, we back up 3 feet and collect.
That was somewhat evident.
So this distance was actually calculated, and we actually hit almost exactly what we were expecting for weight, which was pretty cool.
Are you showing something? Because I don't think we can.
You're not seeing the YouTube app play?
It's on my other one.
Yeah.
You were saying that you hit exactly what you expected. Is that your expected collection amount?
We didn't hear that question very well.
What kind of density did you use to when you calculated how much you were expecting to take?
Yeah, so you can figure on around 1.6 grams per cubic centimeter.
That's pretty close to what it comes into in the bucket after you mix it up.
It entirely depends. Like, even just the humidity down there, 2 years ago it wasn't too humid and it flowed really well. Last year it was pretty humid and it stuck in our bucket hopper a lot more than we had anticipated. So right here, the plan was back up about 7 feet and spin around looking for the navigation target. This should have been a flat area, but it was at a very slight incline. So the laser, which was just a fixed mount laser, was suddenly going up and over the navigation target slightly.
Front head with you.
So we let it spin around like 7 or 8 times, and then we took over manually at 3 minutes and 23 seconds, I think.
We can't see your YouTube video, but I think me and Michael have seen the video prior. But,
Oh, you have to use the YouTube app, but there's the link.
I thought
Sorry about that. If I had known you didn't have the video playing while I was watching it, I would have changed how I did that.
It's fine. Yeah.
Michael's got it figured out. So can you all see the YouTube video now?
Yeah, we can see it.
Alright. Also, have you guys checked out the video, all the videos from the last competition? Because they're all on Ustream.tv.
Ustream.tv. I don't think we've only seen what was on YouTube.
Alright. So Ustream.tv/NASA Edge. And you'll have to go back a little bit in the history, but it should still be pretty close to the top. I can get you a better link in just a minute.
So you were talking about you had a laser that went over the. You had a pin on the bin.
The retroreflective target, so it sends the laser directly back where it came from,
Yeah.
and then it picks it up.
You had a retroreflective target on the bin.
Yeah.
How much did you guys just mine when you dumped?
The first collection was 30 kilograms.
So we just saw you dump 30 kilograms?
Yeah.
Now, earlier you were talking about you hit it right on your expected. So you guys modeled your expected collection rate.
Can you talk into the microphone a bit better?
You guys were talking about how you collected right around your expected. Does that mean, how did you guys model your expected collection rate?
Oh, that was
Based on dig depth.
pure geometry. So dig depth, distance, and width of the bucket.
Oh, okay.
Yeah. So we just assume ideal efficiency, and we were able to mine out that rectangular hole basically,
Yeah, yeah.
and that was pretty close. I think we were expecting in the 30, 30 plus or minus a couple, and I think we got 29 or something like that.
What was the density you had when you dug, approximately? 168?
Can you say that again?
What was the density of the soil when you had dug it, approximately? 168?
So it's somewhere between 1.6 and 2 grams per cubic centimeter, depending on how much it's packed down and how humid it is.
So that's gonna be a variable that you'll never know.
Okay.
All you're gonna get is the basic range. They'll never tell you anything else.
Yeah, yeah.
I mean, because other people are mining, you go after several teams, and they try and pack it down a little bit, but that doesn't mean a whole lot necessarily.
Run your numbers on at least 2 grams per cubic centimeter when you're figuring like your linear actuator and everything.
Oh, yeah.
If you run them all on 1.6, like theoretically it could be fine, but just as easily you could
Always pick it.
yeah,
Yeah.
could have some big issues.
What kind of linear actuator do you have? Specs on it? Linear actuator do you have?
It's a ball screw. Is that what it was?
Yeah, we got it from Motion Industries. It's ball screw, 500-pound dynamic load, which was probably overkill for last year, but they only saw them at 300 and 500, so it was what we needed.
What kind of moment did you have?
We on our tracks, we started out with bag motors from Vex Robotics. We toasted those on our practice run, so we switched to mini sims, which are a bigger DC brushed motor. On the conveyor, we actually have 2 counter-opposed bag motors from Vex. So one was powered backwards, so they go the same direction. Then I think we also put a mini sim on the linear actuator. we actually had to remove the factory motor and then create a new mount and everything.
This is Nathan. He's been doing a lot of our big counts for us. I think it's much fun.
Where do you guys do your testing, and how do you test your theoretical with your experimental? Like, what do you guys do specifically with that?
Do you have a pit set up somewhere? Big sand?
Yeah, give me just a minute. I can show you what we've got. I'm just going to add my phone to the Google Hangout.
Okay.
The material we use, it's a combination of Portland cement, fly ash, and silica sand. I believe it's 6 parts Portland to 531 Portland fly ash silica, and that has very similar properties to the BP1 that they use.
If you check out David's phone, he is looking into the arena, I believe.
Oh, sorry, I had screen rotation off.
We just had it. We lost it now.
There we go. So this is your.
So this is our. We have about 5,000 pounds, I think it is, of the material that. So this is about a 10 by 10 section or so. Nothing too fancy about it.
Are you guys pretty careful with that fly ash? Because that stuff's pretty nasty and radioactive.
That's the president of EDT here.
El Presidente.
You guys take the safety precautions when you drink it?
Sorry, can you say that again?
Do you have any safety precautions when you take when you run the tests in your little your facility there?
Yeah, we wear dust masks and respirators and bunny suits. The material is a skin irritant, so we try to keep that off our skin as much as we can. It's not a really, really bad skin irritant, but you can get a rash if you're around it too much.
Do you mind repeating what your particles were, the percentages you used, and what they were again?
Sure. So 5 parts Portland cement, 3 parts silica sand, and 1 part fly ash.
And
It's just silica sand, like it's really fine silica sand.
Like sandbox sand. Sand is the grain size and silica is the material.
Yeah.
We can get fly ash. Yeah, I assume type 1 Portland cement, or probably doesn't really matter.
I'm not. Oh, we bought it at Lowe's, so it's actually
type 1.
I can get us a discount there. Yeah, go ahead.
so my other question is, for ours I used the Bolinol model for 3D excavation digging. What type of materials do you guys use to find your theoretical forces and digging mechanisms?
Brian. It was over my head. So.
Historically, we haven't had a whole lot of analysis, at least not analysis that's been saved. It hasn't really come up as too much of an issue for us.
So you just do experimental and just kind of go with it?
Yeah.
Trial and error? Okay. Yeah, so we're at a loss because we don't really have anywhere to test things, so we're kind of basing all of ours on theory.
I know a lot of teams try sand, which isn't a very good replacement for the BP1 for testing reasons, but it's better than nothing if you're having issues with running an analysis.
It's probably only good for weight. And doesn't really test how the material flows.
Yeah, it doesn't give you the behavior, but it might give you some accurate, at least, ideas of the force. So, for dumping especially, I wouldn't rely on sand behavior for.
We tested it in the sand on the beach in Florida, If you get too wet of sand, then it's way heavy, much heavier than you'll probably experience in the competition.
You're also dealing with a different grain size, of course.
With a different what?
With a different grain size, of course.
Yeah.
And, you know, internal it's completely different. Well, you guys gave us a tour. Would you like to see a tour of our shop?
Yeah, sure.
All right. We'll take you around. Which guy? All right.
Look at Michael's Bailey's.
Alright, yes, that's good.
Would you run a little bit of design competition? Okay, try to get through. We do a lot more than RMC here.
Can you guys unmute the microphone on? Yeah, there you go.
There we go. Yeah.
And then mute the other microphone.
Yep. So we do a lot more than just RMC here. We have the bottom chassis for the IGVC, Intelligent Ground Vehicle Competition here. There's, looking at it, that's the upper portion of it. These are the JSTC, which is can't really speak too much on it, but in a couple of robots. Another one.
Yeah, so they do a competition where they pick up cones and deposit it. So we're trying to combine all these different little robotic projects into the NASA, hopefully.
This is our Bridgeport here. Most of our machining is done here. It's all manual, no digital readout, nothing. So kind of difficult. So yeah, this is the machine shop. This is a portion of the robot we have finished already.
So this is a steel frame, correct?
Everybody's there. Yeah. Chromoly 4130.
Cool. Did you guys look at using an aluminum frame for their main frame section that you already have?
We
were looking at aluminum, but
we don't have a way of really welding it, and most of our experience here is with square designs, at least.
Sure.
So we were trying to use the chromium alloy steel, so you drop a wall thickness and you coat something which is similar to the aluminum extrusion, which a lot of teams use.
It's really light.
So I'd say we're probably comparable, if not a little less, than the extrusions that people use, but I'd say you guys probably got to be pretty bad with your tubing.
Yeah, we don't really have anyone who can. We don't have the facilities to do aluminum here. We would have to source it all out. Whereas with the chromoly steel, we can do it all in-house in our Bridgeport.
Sure.
We have had experience in the past with aluminum tubing, square tubing, that was welded in our machine shop here, but
8 hours.
Yeah, it took an exorbitant amount of time. And, it didn't. I mean, there hasn't been any issues with it, right, Michael? But, with the aluminum robot. But, all right, you can see it. Yeah.
I'll go grab it. Bring that.
Out of curiosity, how much does that section there weigh? It's 31.5 pounds.
Without the motor.
So
31. Yeah.
39 pounds about. Kilograms.
Yeah.
About 40 pounds with the motors and gearboxes. So
What can you tell me about the motors that you guys have for your drive system?
All right, so what we did is we used, I don't know if you've looked into it, there's this Becker model, which I guess was developed and the military uses it, it's for tanks. So we were doing a little research on how to drive on deformable terrain. We picked the specs off from the NASA docs, and then we got our, because you know, I went there with Oakland Community College, and one of our big problems was we spec'd our robot to drive like on the normal terrain and then put a factor of safety of 2, and we thought we'd be all right. But as you know, that did not work because it's hard to drive. So what we did is we found that when driving on the soil, it's a little bit different. You get it gets broken down into 2 forces, compaction resistance and bulldozer resistance. We ran our numbers on our expected weight of the bot. We kind of went overkill and we said it would be 200 pounds to be safe. And then we ran our numbers based on our wheel width and the properties of the material, and we found the forces that would be required to accelerate to our driving speed and then drive. And then we spec our motors to have a current draw that our motor controllers can handle, which would also be fairly low, so we could be low on our energy consumption. I know that's a part. We pulled up motor curves, pulled up our gearing, and saw where we would fit in there. We actually have a doc about how we did it, but expected like that. We found our expected, and then we designed for our expected, and that's what we came out with.
yeah, specifically about the specs on the motor, we have a 101 planetary gearbox here. And it's made by Dynamic Systems. We have a brushless, brush servo motor, 24 volts, 6.1 amps, 6.1 amps rated, no load. I did the screen share if you want to pull up the UIC. Here. This would be the so it's the MS22 30, so it's the 145 watts. And we have encoders on the rear of them for future autonomy. It's got 100-to-1 planetary gear. And it wasn't cheap.
You said those are brushed?
Yes. And brushed.
What are you using for motor controllers? Just curious.
We have a Robotech. Offers a
Hey, John.
decent.
We got our electrical here. Talk about it.
Yeah, let me pull up
What do you want to know? We're talking about Robotech, my friend. Yeah, give me
stats on the Robotech.
And those are probably, I'm assuming those are brushless only though? I mean, brushed only?
Yes, they do offer brushless.
They do operate with brushless and brush modes. There's 2 separate configurations. Yeah. There. Robotech motor controls there. They're multifaceted devices. They're capable of doing basic PWM input, RS-232 inputs, USB inputs, pulse input through for like an RC controller, and then scripted. So they act as an embedded drive control system along with being a motor controller. So they minimize our design. So that's what really is what really prompted the research into them and the utilization for this design.
I pulled up a data sheet. This isn't a particular model we're using, but it is of this brand.
No, this is one of them.
Yeah, we do have one.
It's only a dual channel.
And our,
This is a single channel.
yeah, single channel one is being used for our digging mechanism. That's the control of that.
Yeah, they do have a dual channel Robotech in a single package. Yeah, it's kind of nice. What do you guys use for motor control?
The last couple years we've just used RC grade motor controllers from Castle Creations. So the Mamba Monster and the Mamba Max Pro. The Mamba Max Pro do brushless, and I'm looking at another RC brand that is very similar for brushless motors. And that's just basically PWM,
Yeah.
but only.
How do you?
Well, John,
This is our electrical.
actually, I guess I'm just curious. So in the past, how have you done your 802.11 BG wireless communications for the competition?
We have, so what you do is you have your router is going to be hardwired to the NASA network on the edge of the pit, or the arena. And then we have a wireless bridge on the robot. So that just basically connects wirelessly and extends your network, so we could plug hardwired devices into it. So so we'd have like a computer or something. Last year we used National Instruments single board Rio, which is just basically a real-time computer.
Okay.
They plug it in like a normal network into the bridge.
All right. So you're just using a router on each end essentially. One for an access point, and the other end is just to act as a client.
Essentially. So we have a router and a bridge. So the bridge it's not actually a router. It's designed specifically to be a bridge or an access point, actually.
Yeah, it's basic configuration. Yeah, because with our design, we're actually having a wireless microcontroller that's our signal multiplexer or our selection unit that allows us to identify what device is currently operating in. If it's going to be on an autonomous mode, a remote control, or in a safe mode where all the safety signals are sent out so the device is not operating. Ours is operating off of the Texas Instruments CC3000 from Adafruit specifically. It actually allows us to minimize data consumption. So, I mean, with basic PC, one of the overhead concerns we were worried about was throughput. So, did you have any issues with that on your end? Was throughput ever what were your average network consumption speeds?
I don't think did we get those numbers? NASA. I think NASA keeps track of that for bandwidth usage. I know the first year that I was involved, which was 2 competitions ago, we actually won the Efficient Data Communications Award. So what they do is they take the average average kilobytes per second throughout the whole run and divide that by how much you've mined, how much you've collected.
Oh, okay.
So we won that award that the first year that I was here. No, it's still there. But last year we didn't get that. I switched to a system that probably had a little more overhead on its communication. I was using LabVIEW, so I used some native functions that probably had a little more overhead on them. So our data consumption was higher last year than it was the year before.
Okay.
Sorry, we didn't get your name.
I'm Nathan.
Hi, Nathan. So how much data are you guys sending? I mean, so you have to control, what, 4 motors, right? How much data does that cost you guys each time you want to update your motors?
I don't have those numbers for our last year's robot. Mostly what we did was, we programmed it, and then we tried to just monitor the bandwidth, and we were way below any values that we were concerned with. So I don't know those numbers off the top of my head.
Do you happen to know how much resolution and control you had over your motors?
No, I'm not sure what numbers would satisfy that question. I know. Well, and what I can tell you is that we had closed loop feedback in our SB or single board Rio, which is an FPGA device. So we had closed loop feedback for speed on our tracks. And so I just told it, go this fast. That's probably not the answer you want, but that's all I have.
All right, so there were two more topics I'd like to hit. Obviously, one thing I think that's really cool about this NASA competition, the outreach. It's kind of cool that we get to bring this and promote STEM to the kids. And you guys were talking about how you guys actually very successful in that in the past. So maybe a few words about what you've done for outreach and how the importance that you think it has.
So we do tons of events every year. To put it plain and simple, 2 years ago when we got first place, we won. We had, I think, 17 events that we attended throughout the year. Last year we had 19 or so, and we got third place, but we got first place out of all the American teams. And since this year it's American only, I think that counts for something. But what ended up happening is Bangladesh is the same size as Iowa, like really, really similar, but they have 50 times as many people. So their numbers just looked fantastic. Like thousands and thousands of people reached out to.
Another thing was mission.
Yeah, they also went to neighboring countries, but being in landlocked little Iowa, that's obviously impossible. But as far as events that we do, we'll go to the state fair. That's a good way to get a lot of impressions on what we do. There's something called the Iowa STEM Council, who I think every year they hold 6 events in 6 regions of Iowa, promoting STEM. So we've gotten to a couple of those. We'll do school visits, help out a little bit with we'll do demonstrations at the first LEGO League state championship. Those are some of the events. Do you have any more specific questions about outreach then?
No, I mean,
I think that's pretty much. You do some first robotics, go to schools. It's about similar to what we were looking for.
And maybe a few comments on the importance of the outreach in your opinion.
Sorry, I didn't hear that.
Maybe a few comments on the importance of outreach in your opinion, because this competition, I think.
Competitively, or
no, as an engineer. As an engineer, I don't know.
Yeah. So as Nathan and Brian are pointing out, overall in the competition, it's not required. But if you want to go Cosmo board, you really have to have outreach. So not only from that standpoint, but just just how you show off what you've been doing to the community, get the word out about how you what's happening on campus. So even disregarding the fact that you're trying to get next generation of scientists and engineers interested in the field they don't know about, it's a great way to demonstrate what you do. Also, you can pick up sponsorship just by going out to the community. Last year I think we estimated somewhere around 19,000 people saw our robot at outreach events cumulative. So between that, we picked up a lot more outreach events, and it really looks at the sponsors when you get your robot with their logo out in the community.
We have Leslie, she runs our outreach. Leslie, would you like to say a few words?
I can't hear you.
It's fine.
Well, if you want to, give a shout out to some of the schools we've been to, we're working with that.
So far what we've done for our outreach efforts is we went to my old high school, and we also collaborated with our ASME chapter here in UIC, and went to one first robotics coaching event. And then right now I'm trying to set events and have kind of like a demonstration of our robots, as well as have workshops. And then other stuff we were trying to do is work with this foster. Well, it's not a foster.
Well, we're working with Society of Hispanic Engineers, and we're going to bring some kids to UIC, and we think that's going to be a really great event. And
since we don't have a robot currently built, this is our first year. It's kind of difficult.
We are using our robots for the other competition, which.
Yeah, I mean it's not going to be the RMC robots, but next year we should be able to at least showcase our robots a little bit sooner.
Yeah.
It's year one. I mean it's difficult to get everything built, designed, and have that stuff.
One thing that we've done that was very popular, if you have like little RC kits, what we've done is we'll set up a little arena and give kids like different components that they can add on to their RC car, and then we put a couple of ping pong balls in there, and they play RC soccer. So you put a big bumper out and run into all the other cars, but you can catch the ball from anywhere. So, so to speak, we can use robotics that we've been to use for that.
Good idea.
It's a great idea. Well, we were planning on having this run for like 15 minutes. I think we've kind of overgone that time limit, but I don't know. In years past, NASA's put a big influence on cultural exchange. Now it's kind of national, but if we ever end up in Des Moines, what are some cool things to do, or a cool factoid about Des Moines?
Go home.
Not in we don't know.
Yeah, we're not in Des Moines.
So we're actually in Ames, which is about 30 miles north of Des Moines.
Oh, sorry about that. Or we'll edit that out. That's
if you're in Des Moines, there's a place called Zombie Burger, which is really good. They've got
One of the best things ever.
all sorts of like specialty burgers that you'll get like peanut butter or fried egg burger, and it's amazing. The ISU Fair is something that you can do. It's pretty good. There's a lot of Anything else?
No.
What?
No.
Yeah.
That's what this was.
We actually have a pretty good view of the garage door here.
yeah. Oh, I closed mine.
All right, I'll grab this one. Okay. Pull it up.
Here, we're going to show you right outside our garage door. We kind of have a good view of the Sears Tower, so we thought maybe we'd show you that. And we can also exchange burger joints if you want.
Yeah, we have plenty of good places to eat.
Yeah, milk.
Just look at Michael Metzger's view.
So out here, that's the Sears Tower, and that's kind of Willis Tower. Sorry.
You guys still call it the Sears Tower?
Yeah, they're both everyone calls Sears Tower.
So, what part of Chicago are you guys in?
We're downtown.
Okay.
We would be technically considered west. It's practically downtown. By all metrics, it's down.
Oh, and for so we got the Sears Tower, and you guys gave us burger recommendations. So we got Jim's.
No, don't go there. There's Portillo's. You might have heard of.
Portillo's.
Is it pizza?
Yeah, we got a bunch of.
We got the best pizza.
We got the best pizza. We got Chicago pizza.
We got Portillo.
I'm at the pizzeria every time I go to Chicago.
What's that?
I go to pizzeria every time I go to Chicago.
Pizzeria.
Pizzeria Uno.
Try Lunabotics. Try
Giordano's, Lunati's.
Lunabotics has a great butter crust. You gotta at least try it once.
Lunati was my gypsy, right? Yeah. All right. Well, thanks for stopping by.
We'll upload this to YouTube. Probably check Chicago EDT.
And yeah, we'll upload it. We'll probably do an edited version, like cut it down so it's like watchable. And for that, would you like to do any shout outs at the end for your sponsors?
Yeah, shout out to Vermeer, SLTI, our motor sponsor for the year. Alcoa. Oh, I'm skipping a bunch. John Deere, Caterpillar, National Defense.
Alright. We'll figure it out. Alright, so design it, dig it, build it, or whatever. Thanks for hanging out with us, guys. I look forward to meeting you guys when we go down there.
Yeah, sounds good.
Alright, thanks.
All right.
Hi, thanks for watching our Hangout with ISU. We'd like to take a minute to thank our sponsors, AMD Semiconductor, Ford PCB, Hemisphere GPS, Here Maps, and UIC College of Engineering.
Go Flames!